Okay, so this is the first part of a four-part mini course by Sander Kupers on homological stability.
Okay, thanks for the invitation to talk. I'm glad that there's that many people interested in this topic. So let me start by telling you what this mini course is going to be about, what I'm going to do. So I'm not going to go straight into like the cutting edge homological stability technology. Rather, my goal is going to be to explain one example, the easiest example of symmetric groups, in a lot of detail, so you know exactly how at least one homological stability argument goes. Then I'll talk a bit about how one can generalize that argument to other sequence of groups. And then only in the last lecture will I talk about more subtle stability phenomena like representation stability or secondary stability. So the goal is that you go away with a sense of how you might go about proving a homological stability result and what they might be useful for. So today the focus will be on the homology of symmetric groups. So we all know what a symmetric group is, right? Sigma n will be the permutations of the set with n elements. I'm just fixing some notation here. And how is that defined? Well, in this mini course, I'll define it through the classifying space. So whenever you have a discrete group G, there is a space BG, which is determined uniquely up to homotopic equivalence. By demanding that almost all of its homotopic groups vanish, except by one. So I'll keep suppressing base points because all my space will be connected. So it's 0 most of the time, except by 1 is equal to G. Okay, so how is this constructed? Well, there's many ways of doing it. You can take any contractible space with a free properly discontinuous G action and take the quotient. But it will be convenient later on to take the following model. So what you can do is extract from G a category. So we have this group G, and we can build a category. In fact, it will just be a groupoid. Then I'm going to call star mod mod G. And it has a single object called star. And it has morphisms from star to itself, indexed by the elements of the group. And the composition is given by multiplication in the group. And the identity is given by the units of the group. Okay, and once you have this object, you can build a space out of it as follows. You can take the nerve to get a simplicial set. So its P simplices will be given by just strings of P composable arrows in your category. So they're just given by P elements in your group. So this is a simplicial set. And then you can take the geometric realization. Now, we won't really need the details of this construction in this lecture. We will need it in the following lectures. So if you're not familiar with this, in the webpage that I posted, there's some references where you can read about these constructions. Okay, one thing I should say, the lecture notes will have exercises, lots of exercises. And one of them is proving that this is indeed homotopic equivalent to BG. Okay, so we can apply this construction to the symmetric group. And then ask the following question. What is the homology of the classifying space of the symmetric group? Maybe as a remark, this is the same as asking for the group homology with coefficients in Z. If that's something you're more familiar with. Okay, so, well, in some sense, a complete answer exists, but I'm not going to give it to you. But just to get a sense of what it looks like, let's do some examples. So easy cases are n is 0 and 1, because in this case, this symmetric group is just a trivial group. Okay, so there's nothing to prove really. For n is 2, we have that the symmetric group is isomorphic to the cyclic group on 2 elements. And the classifying space, well, we need to find some topological space that has all its homotopic groups vanishing except by one, which has to be C2. And that's RP infinity. So you probably know how to compute the homology of RP infinity with integral coefficients. Let me just give the reduced homology. So I'm removing the Z in degree 0. This is Z mod 2 for star greater than 0. I guess I can just say star, yeah. Star greater than 0 odd, and it's 0 otherwise. I guess I don't really need to say greater than 0. Okay, so that's pretty easy. Let's do one more, which is n is equal to 3. So this is a dihedral group, D3 with 6 elements. So the symmetry of a triangle. And by taking, for example, this CELOF3 subgroup and then constructing a Schrödinger sequence of groups from that and looking at a Serre spectral sequence, you can compute the homology of this group, or equivalently of its classifying space. And the answer is Z mod 2 if star is equivalent to 1 mod 4, Z mod 6 if star is equivalent to 3 mod 4, and 0 otherwise. So as this, both the answer and how I outlined how you might go about computing this indicates, this already gets pretty complicated and it becomes quite hard to by hand do these computations for increasingly complicated symmetric groups, even though an answer does exist in some form. So to get a sense of what it might look like in general, the homology of the symmetric group, I want to look at a table that has the first 6 homology groups of the first 7 symmetric groups in it. Okay, so I should be able to do this sharing. Okay, so this is a table. What you see on the x-axis is n. That's the index of the sigma n. And on the vertical axis, you have d, which is the degree of the homology. Okay, so these are the first couple of homology groups. I had to somewhat unnaturally combine some into two particular groups. So there's a few things you can notice about this, and I'll point them out. in a minute, but maybe you want to stare at this now, just get a sense of what it looks like. So the most important feature from the point of view of this mini course is that in a range that increases with n, these homology groups don't change. So that's on the next page, if I manage to get there. So on or below this line, when you move in increasing n direction, so you go horizontally, the homology groups don't change anymore. That's the most important feature that you might observe when you look at these tables. Okay, so let me write down that feature, but a couple of other ones you might also have noticed, since they will be interesting when I talk about applications. Okay, so the first thing is that all these homology groups are finite, as long as you don't look at degree 0 or you take reduced homology. That's maybe even more fundamental than the thing I just mentioned, which is that in fixed degree D, the homology becomes independent of n as n increases. Now, there's a couple of more that when you go back and look at the notes, you can observe, which will be interesting when I look at applications. So the first one is that the homology only increases in size. So the groups become larger and larger. They never become smaller as you increase n. Some of these are a bit imprecisely formulated, and what we'll do in a second is formulate them more precisely. And finally is that the p power torsion only changes when p divides n. Okay, so I recommend before the next lecture, you look at these tables again and see that these things indeed occur. Okay, but as I said, some of these are not formulated very precisely, particularly the last 3 are not formulated very precisely. And that's because, in some sense, in these statements, only comparing these groups as abstract abelian groups. And that's not a smart thing to do. It's better to have maps between them. So I'll define those now. Okay, so the n element set, of course, sits inside of the n+1 element set. So whenever you have a permutation of the n element set, you can extend it to the n+1 element set by the identity on the new element. Let's call it sigma. Now, one reason to give this construction of BG in terms of a category whose nerve you take and then you geometrically realize is that it becomes clear that it's natural in groups and homomorphisms. So we get an induced map that I'm going to denote by sigma as well on the classifying spaces. And this then induces a map on homology groups. And the better formulations of these last 3 points are going to be in terms of this map. Okay. So the second one, which says that the homology is independent of n as n goes to infinity, that should become the statement that these map sigma star are isomorphisms in a range of degrees tending to infinity with n. Okay. If that's the case, then any fixed degree eventually is in this range, any fixed degree d. And so all these groups are going to be the same as you increase n. So the third statement, which was that these groups don't increase in size, is probably better formulated as saying that sigma star is injective. And the fourth one, which is about the p power torsion, is that sigma star is an isomorphism on p power torsion, unless p divides n plus 1. Okay. So all of these properties are true. All these things we've observed in the tables: 1, 2 prime, 3 prime, and 4 prime. In fact, both 1 and 4 prime have the same source, which is an argument using transfer maps, which is one of the exercises. Which is the following result. If G is finite, then if you take the reduced homology of BG, but you take coefficients in which you've inverted the order of the group, then that's 0. And as a stronger statement, when you have a subgroup G of H, in that case, you can say that the homology of BG with coefficients in Z, where you've inverted the index of G and H, this is a retract of the homology of BH with those coefficients. So the first statement follows by applying the second one, with H being just the identity element. Okay, so 2 prime implies 2 implies 1. And to deduce 4 prime from 2, just observe that the index of the symmetric group on n plus 1 elements, sorry, the subgroup of the index of subgroup of n elements into n plus 1 elements is n plus 1. And as a consequence of the long sequence of, oh no, it's probably easier. I mean, you get now that, yeah, let me maybe not go into details. Maybe let's make this an exercise.
May I ask a question?
Yeah.
What do you mean a retract between homology?
Oh, that's why I made this an exercise, because I should have made a stronger statement that There's a natural map given by including the group. Yeah, what I mean is that there is a there are maps both ways, such that when you take the composition starting and ending at the homology of BG with these coefficients, that's the identity. So in other words, the homology of BG with these coefficients sits inside of the homology of BH as a direct summand. And one of the maps would just be given by the inclusion of, will be induced by the inclusion of BH into BG. The other one would be a transfer map. But because I didn't state it with those maps, that's why I wanted to make it an exercise. Okay. Does that answer your question?
Yes, of course.
Okay. So we'll use this in a couple of applications in a minute, but it's really property 2 and to some extent property 3 that are of interest in this mini course. So let's give a name to that. Okay, so suppose you have a sequence of spaces and maps between them. Okay, you should think these are B of sigma n, and sigma is that map I just defined, which we usually call the stabilization map. This exhibits homological stability or satisfies homological stability, if you prefer that way of saying it. If the induced maps sigma star from the homology of xn to the homology of xn plus 1, if these are isomorphisms in a range tending to infinity with n. Okay. Now, in practice, you're going to want to give an explicit formula for this range. Makes it easy to apply such a result. There are some examples where you maybe want to vary the coefficients. We'll talk about that in the next couple of lectures. Okay. So the goal for at least the next lecture and a half is the following theorem. So I think it's fair to attribute it to Nakaoka, but he proved much more than this. So the statement is that it's indeed true that these classifying space of symmetric groups exhibit homological stability, and they do so in the following range. So the induced map are isomorphisms are surjections in the following range. So star less than or equal to n over 2, and isomorphisms in a slightly smaller range. So this is a type of statement you tend to see for your ranges, is surjection in a slightly larger range than isomorphism. What this is hiding is that maybe you should be looking at the relative homology groups of the map sigma rather than the map it induces. But this is maybe a more elementary way of phrasing it. Of course, since we know by this third property that all the stabilization maps are injective, actually the range is slightly better for the isomorphism. Right? Because if you're a surjection, that's also an injection, you're an isomorphism. Okay. Now, property 3' is rather special. It's something that you only should expect to hold for classifying spaces of certain finite groups where you can construct transfer maps. But again, I'll use it in some applications in a minute. There will be an exercise where you prove property 3'. I should also say that with this slightly improved range, that's the optimal one among linear, affine linear ranges. Okay. So it's really true that this theorem is going to be the goal of the next lecture and a half, because for the remainder of this one, I want to talk about how you might use homological stability for symmetric groups. Of course, a sequence of groups or a sequence of spaces exhibiting homological stability is an interesting structural property to prove. And there are papers that just do that. But I think it's also important to keep in mind that it's a useful tool to prove other mathematical results. And since I imagine that a large part of the audience does not routinely think about homological stability, I think it's important to highlight some of those. Now, the examples that I'm going to give here are going to be things you can prove maybe with other more elementary methods. But for other sequences of groups or spaces, there's similar applications of homological stability that I don't know a different proof for. So these things do serve as blueprints for other applications. And they will all have to do with the following idea. It's that homological stability can transfer information from finite n to infinite n and vice versa. So let's start with a very complicated proof of a elementary fact in group theory, which is something about alternating groups. Okay, so suppose you have a path-connected space X, then the Hurewicz map for pi1 is a map from the fundamental group, I'm suppressing the base point, to the first homology group. And since homology groups are abelian, this factors uniquely over the abelianization. And then the theorem is that that map is an isomorphism. Okay, so we can apply this to the classifying space of the symmetric group. Okay, so what do we get? We get that the symmetric group maps to the abelianization of the symmetric group. And then maps to the homology degree 1 of the symmetric group. And this is an isomorphism. So what this tells you is that if you could understand H1 of the classifying space of the symmetric group, you are equivalently understanding the abelianization. So we'll use this to figure out what the commutative subgroup of the symmetric group is. Okay. So to do that, we use the sign homomorphism, which goes from the symmetric group to the group on 2 elements. Right? It takes the identity element as value on even permutations and the non-identity element on odd permutations. So this induces a map on classifying spaces, and hence a map on homology, in particular, homology in degree 1, which is easy to compute in the case of the cyclic group with 2 elements, because it is abelian. So the abelianization just gives you the same group again. So let me write that as Z mod 2. And maybe it would have been better to write Z mod 2 for the target. Okay. So we have a map like this, and it's not so hard to check that it's compatible with stabilization, just because the sign homomorphism is. Oops. So you get a commutative diagram as follows. Okay. Now, what can we say about these vertical maps? Well, the sign homomorphism is an isomorphism when n is 2. So this map on H1 should also be an isomorphism. So when we write down, starting from the second symmetric group, this sequence of homomorphisms, the first one is an isomorphism. And the bottom maps are all equalities. By the homological stability result, we know that this map is a surjection, and from there on, these maps are isomorphisms. Okay, but since this composition is an isomorphism, in particular, this map is also an injective map. So in fact, it's also an isomorphism. So the conclusion that we can draw is that the sign homomorphism from the symmetric group to Z mod 2, this is the abelianization. Okay, which you can also rephrase as the commutative subgroup, so the subgroup of the symmetric group generated by commutators, is equal to the kernel of the sign homomorphism is the alternating group. So we've proven in a very complicated way that the alternating group is the commutative subgroup of the symmetric group using homological stability. Now, Of course, this is a fact you already knew and probably know how to prove in a very elementary manner. And we could have used it to instead show homological stability in degree 1. But now imagine that you have a much more complicated group, like a mapping class group of some high dimensional manifold or something. This actually is quite a useful way to determine group theoretic properties of groups like that. Okay, so that's one application. The second application I'll give will be to stable homotopy theory. But to do that, we have to first talk about group completion. Okay, so let me rephrase homological stability in a slightly different manner. So a map that always exists is the map from the homology of the end symmetric group to the co-limit over the stabilization maps. Okay. Let's call this a stable homology. Now, what homological stability says is that this map is an isomorphism in a range tending to infinity with n. Is there a question? So this has the following somewhat tautological consequences. One is that you can use the stable homology to get information about the homology of some symmetric group. Or you can use the homology of the symmetric group to get information about the stable homology. And this would not be a useful statement, or probably not a very useful statement, unless we had a different description of the stable homology. And luckily we do. So the most useful homological stability results, at least in my experience, are the ones where you also have a description of the stable homology in terms of homotopy theory. In fact, stable homotopy theory. Okay, so when we constructed the stabilization map, this map sigma, what we used were just the inclusions of an n element set in an n+1 element set. This was given by taking the disjoint union of the n element set and one more element. But of course, you can also take disjoint union with 2, 3, etc. elements. So more generally, disjoint union gives homomorphisms from a product of symmetric groups to a symmetric group on the sum of the two indices. Now, that induces a map on classifying spaces. And you should think of these as multiplication maps. But not multiplication maps on just these individual symmetric groups, the domain that the target wouldn't line up, but as multiplication maps on the disjoint union over all n of the classifying space with a symmetric group. Now, why do I call them multiplication maps? If you suitably model them, This is part of the structure of a unital topological monoid. Which is also homotopy commutative. Okay, maybe it would have been better to say E1 space, since that's a homotopy invariant notion, but maybe you're not familiar with that. Okay. So let's look at one of the consequences of this. Well, one of the consequences is that pi 0 of this space is a unital monoid, which is also commutative. And what is it? This is just the natural numbers with the usual addition. Okay. Nothing super exciting. But we'll use this crucially when identifying the stable homology. Okay. So the stabilization maps that we had originally between just classifying space of symmetric groups induce a self map of this disjoint union, which maps the n term to the n plus first term. Okay, you can think of this as multiplying with an element of b sigma 1. And the result of that is that the homology of this disjoint union becomes a module over z of pi 0. So the free abelian group on pi 0. This is just isomorphic to a polynomial ring. Okay, so now I can finally make a statement about the stable homology. So computing the stable homology is the same as picking out one of the summands of this colimit. I just get an z's worth of the stable homology. But another way to compute such a, what does this colimit compute? It computes the localization at pi 0. Indeed, there is a map from the homology to the colimit. And in the colimit, pi 0 becomes invertible. So it factors like this. And this is an isomorphism. Okay. And the point now is that the McDuff-Siegel group completion theorem tells you how to compute this. And what it says, roughly, is that you could have inverted pi 0 on the inside of homology. Of course, you have to make that into a precise statement. Okay, so what is the precise statement? Let me phrase it for M, a homotopic commutative unital topological monoid. Then says that the homology of M inverting pi 0 is the same as the homology of the loop space of the classifying space of M, which I'll define in a second. But you think of this as a homotopical way of inverting pi 0. Okay, and I'll spell out in a second what this gives for the symmetric groups. But maybe from the way I've presented it, you can imagine that if I had a different sequence of groups, I could, under some minimal properties having to do with the existence of these types of direct sum maps, I could try and run a similar argument to try and compute the stable homology. Okay, so I have to tell you what loops of BM is and then give you the answer in the case of symmetric groups. So, I mean, loops is just base loops at some base point I'm going to give in a second. BM is very similar to the construction of BG. Okay, what you do is you build a category. Well, it's now going to be enriched in spaces, which means that it's going to have a space of morphisms rather than a set of morphisms. And how is it going to be built? Well, very similar to the construction of star mod mod G. There's going to be a single object, star. The morphism space is going to be given by M. The composition is going to be multiplication in this monoid. And the identity is going to be the unit of the monoid. We don't need that as homotopic commutative here. Now, strictly speaking, oh, well, okay, and then you do the nerve and you take the classifying space. Strictly speaking, this is not exactly the correct homotopy type unless I assume that the inclusion of the identity into M is a cofibration. Oh, but let's not worry about that. And the canonical base point is provided by the object star, and that's where the loops are going to be based. Now, the point is that there's many techniques for understanding BM, or spaces that look like BM. These are like delooping machines, infinite loop space machines. And in particular, you can apply them some of them, many of them, apply to M, the disjoint union of the classifying space of the symmetric group. And what you get is the following theorem. You can think of this, if that's something you're familiar with, as a zero-dimensional case of the computation of the homotopy type of the cobordism category. Symmetric groups are the diffeomorphism groups of zero-dimensional manifolds given by endpoints. Anyway, so it may be a generalization of this is the Matson-Weiss theorem. The answer is that loops B of disjoint union of the classifying space of symmetric groups is homotopy equivalent to the infinite loop space of the sphere spectrum. Okay. So this is the sphere spectrum. So it's a sequence of, well, I guess I'm not going to go into, it's not going to be super helpful for me to define what this notation means because you either have seen it and then you know, otherwise it's going to be too fast. Let me instead say what its homotopic groups are. So the ith homotopic group of this space based at 0 is the same as the ith stable homotopic group of spheres. So you take pi I plus k of sk, and then let k go to infinity by taking suspensions of the domain in the target. Okay, so the upshot is that the stable homology of symmetric groups is the same as the homology of a single component of this space, and hence closely related to the stable homotopic groups of spheres. So in the last 10 minutes, I'm going to use both homological stability to prove things about the stable homotopic groups of spheres, and use stable homotopic groups of spheres to prove things about the homology of symmetric groups. There are probably things you could have proven using more elementary methods, but there's some other examples, which we'll maybe see later, related to like algebraic K-theory, where homological stability results are the only way to prove similar statements. Okay. So the last section is maybe called Serre's theorem and variations. Okay. So let's see. By homological stability for symmetric groups, we have an isomorphism between the homology of the n-symmetric group and the homology of a path component of loops infinity of the sphere spectrum for star less than or equal to n minus 1/2. Now, the first property we discussed says that these are all finite, at least in positive degrees. And by taking n as large as we want, note that this does not depend on n. We just see that the homology groups of this infinite loop space are all finite. Okay. And this is the following consequence. The consequence is that the homotopic groups of the sphere spectrum, which are the same as the homotopic groups of this infinite loop space in positive degrees at least, they are all finite for positive degrees. So there's a little bit to say here. One is something that I've already said, which is that in positive degrees, pi star of S is pi star of loops infinity, 0 of S. The second thing there is to say is that loops infinity of S is a simple space. In the technical sense, pi 1 is abelian and acts trivial on higher homotopy. Every infinite loop space has these properties. In particular, you can do a Serre class argument to prove that the homology, say reduced homology of this space, is finite for all positive on all degrees, if and only if the homotopic groups are. And since we know the first of these statements, the result follows. Now, of course, if you have SER classes to your disposal, you can probably come up with a much quicker argument. But as I said, there's some other examples where one doesn't have that quick argument available. We can do something similar with torsion. Okay, well, why is that? This 4' property tells us that there's no p torsion in these homology groups for n smaller than p. Right, otherwise the p torsion is the same as the p torsion of the previous group, and you can keep going back all the way until you're at sigma 1 or sigma 0. Okay, so the same is to be true for the stable homology, as long as we restrict to low degrees. And let's see, we should be in degree this degree, I think. And now we can again do a SER class argument. Instead of using the SER class of finite abelian groups, use the SER class of abelian groups that have only L torsion for L not equal to P. To conclude that the stable homotopic groups of spheres don't have any P torsion in the range. But of course, a much better range is known than the one we're going to get here. The better range is a result of SER, which says that in fact there's no P torsion for a star smaller than 2p minus 3. And here we can instead argue in the other direction. We can now use that the SER class argument to say that the stable homology has no P torsion in this range, and then use homological stability backwards to say that some symmetric groups don't have P torsion in their homology in certain degrees. So using the argument in reverse, we get instead information about the homology of symmetric groups. And what you get, in particular if you use the fact that the stabilization maps are always injective, is that the homology of sigma n has no P torsion in degrees smaller than 2p minus 3. So this example is supposed to illustrate that maybe things you can prove in a more elementary manner, that homological stability allows you to transfer information between group homology for particular groups and these stable homotopy theoretic objects. So maybe that's motivation to learn how these techniques work. And we'll see some more examples of that towards the end of this mini course. Okay, so that's the end for this lecture. What next time is going to be is the proof of homological stability for symmetric groups. And I think we can almost completely give it, except for one connectivity argument that we'll have to postpone to the third lecture. So that's the example that I want to work out in complete detail so you know how to prove these results yourself. Okay. Any questions?
Okay, first of all, let's thank Sander for the first talk. You can unmute yourself or you can use your reactions or both. And now we'll open it up for questions if there are any.
Yes, I have one question.
Yeah.
Yes. So, is the sequence of symmetric groups exhibit homological stability for any coefficient than just Z?
Yes. So you could get that just by applying the universal coefficient. Well, it depends what type of coefficients you mean. So if you mean constant coefficients, so they're not local systems.
Yeah.
Yes, then it just follows by applying the universal coefficient theorem, or it will follow directly from the proof because the proof will be agnostic towards the coefficients. It is, however, a good question because it can depend quite a bit on the coefficients you take, what these ranges end up being. For example, if you take general linear groups of finite fields, then, so this appears in Quillen's paper on algebraic K-theory of finite fields, you realize that the behavior is vastly different in terms of homological stability for coefficients that have the same characteristic, like finite field coefficients have the same characteristic as the field of your general linear group, or when it doesn't have the same characteristic. Those behave very differently. So it is a good question to think about, could I do something better if I take different coefficients? What you could also do is allow the symmetric groups to act on the coefficients. And in the third lecture, we'll talk a bit about what happens in that case. There's some coefficient systems where, well, you have to make sense of them for all n and have suitable maps between them. But when you do, there's a certain class of them for which you also have homological stability.
Okay, thank you.
Other questions?
Sander, so how does homological stability behaves with respect to, say, taking quotient subgroups, extensions, things like that?
That's a difficult question, and you probably know that that's a difficult question.
Okay, say for
the one thing
like you showed the example of the alternating group, subgroup, like is there homological stability there?
Those have homological stability, yes, and that's because you can rewrite these homology groups as homology groups with certain coefficient systems coming from certain permutation modules, I guess. And these ones are abelian coefficients in this particular case. So I think the precise statement is, to your question is, for extensions, if you know something about, so whenever you have an extension, right, you have like maybe a sequence HN, GN, QN or something. So I think I don't know of any non-technical general statement, but I think, at least thinking about it just now, if you have homological stability for Qn with enough local coefficient systems, then you have a chance of proving it for Gn. Of course, the question is going to be whether the homology of Hn is going to live in a class of coefficient systems where you have homological stability. In certain cases, you can go from Gn to Hn, but only if the quotients are very simple, and in maybe the only examples I know, they're independent of n. So if the quotients do not depend on n, then maybe you have a chance of doing so. But this is not an easy question, I think. Of course, there are a few exceptional cases that you probably know about, which is something like arithmetic groups or something, where you have the work of Borel when you use rational coefficients.
Okay, other questions?
Sanders, do you know if the symmetric group is the first example known that satisfies homological stability?
I can probably look this up to some extent because I made a list for one of the next lectures of almost all the reference that I'm aware of. And so we can just look at. I think it is the first one that I know about based on that list. But it may be the case that some other examples that I'm not aware of existed.
I say maybe UN.
Yeah, there are of course the examples where the homology stabilizes just because the maps become more highly connected. Yeah, those were surely known earlier. Like if you think of something like, maybe think of like Freudenthal suspension theorem or something as a stability result, and those things were much older. But specifically for a sequence of groups, this would be my guess for the first one. But feel free to correct me if you know an earlier example.
Thank you.
Other questions? I have a couple of interrelated questions, and maybe you'll just tell me that it's coming in later talks, and I'll be perfectly satisfied with that. First of all, I imagine that in practice, one often works one prime at a time.
No, unless you're gonna go for like the most optimal ranges, you tend not to work one prime at a time. What we'll see next time is that you don't really use that much about your groups apart from, I mean, your group should arise as like automorphism groups of objects in some symmetric monoidal category or something. That's at least a setting in which you can exactly precisely formulate what you have to prove to get homological stability, and it boils down to a complex being highly connected. And for there to be improvements at particular primes rather than working with integral coefficients, you would have to be in a situation where you can prove that a certain simplicial complex is not highly connected, but is like homologically highly connected when you work with certain coefficients. And that tends to be pretty rare. However, of course, more advanced techniques can give improved ranges if you know something about these complexes, say for low n, where computations by hand are doable.
My other question was, is there a role for higher structure in the sense of, you know, products or homology operations or something like that in all of this?
Yeah, so I'll talk about that in the last lecture.
Okay, that's fine.
Yes, the answer is that you can already see that maybe appearing in this application of the group completion theorem. There's secretly a lot of structure around in the classifying space of these symmetric groups. And the only thing that at least the formulation of homological stability uses is just this stabilization map. This adding of a single element, even though you have this product around, and it's not just homotopic commutative, it's E infinity. So you get all the attending operations that come with that. And so some of the latest homological stability techniques exploit that additional high algebraic structure to get information like past the range where homological stability holds. And it uses exactly these products with elements coming from higher cardinality symmetric groups or other higher n, let me say that.
Okay, last chance to ask a question for today.
You have related the p sigma n's with loop infinity of the sphere spectrum.
Yeah.
What about the classifying space of the alternating groups, B of ANs? Is there anything corresponding in the infinite loop space?
Yeah,
side?
I think that's just infinite loop space of you take like a connective cover of the sphere. I have to think about whether that's exactly right, but that's what it seems like to me. Maybe it's most easily said in terms of the zero component. I think you just replace the sphere spectrum by its like one connective cover where you cut off pi 0 and pi 1. I'm not 100% sure, so you should check the literature, but I'm sure that we know the answer to questions like that.
Is the one connected cover also infinite loop space?
Well, you take loops infinity of it.
Oh, okay.
So I'm taking the cover in the spectra. I mean, it doesn't really matter. I could have taken the loops infinity 0 of the sphere spectrum and taken the one connective cover then. But then it's less obvious that that's still an infinite loop space. You're right.
Yeah. Thank you.
Okay, I think